I will begin with a word of prayer. Heavenly Father, we thank you again for this day, this time we have to meet together. Just pray that you'd be glorified, Lord, in what we do. In my prayer, Lord Jesus. Amen. Like I said, I'll just run through these real quick, and then I'll take your questions. So this one, you're supposed to find the degree and basis over Q of this thing. It's a trap. The trap here is that the square root of 18 is dumb, because square root of 18 is 3 times the square root of 2, so that's already in here, right? So if I extend Q adjoin root 2 root 3 by root 18, yeah, there's nothing to do. So these are equal, so I don't even need to worry about the square root of 18, basically. So then Q adjoin square root of 2 adjoin square root of 3 would be these kind of linear combinations, C1, C2, such that C1 and C2 are in Q adjoin root 2. In detail, that means that it looks like this. Now there's a jump right here, which I'll explain momentarily. I mean, in order to say this, I need to know that the square root of 3 has degree 2 over this field. That's not immediately obvious, right? But it's true by this stuff down here. So C1 and C2 are elements of this field, which means they have this form. And then I just multiply things out. This shows then that the field is spanned by rational combinations of 1, root 2, root 3, and root 6. So at least the set 1, root 2, root 3, root 6 is a possible basis, but we do need to have an independent reason that's linearly independent in order to know it is a basis. Yeah? Oh, okay. Sorry, I was misinterpreting. So, I will, of course, post this when I get a chance, but sometime soon. Here's why I know that this is a degree 2 extension. Because I claim that the irreducible polynomial of root 3 over Q adjoin root 2 is x squared minus 3. Now, how do I know that? Well, first of all, it's the right kind of thing. It is a polynomial that has coefficients in here because, well, Q is in here, right? So, I mean, it's in there. And it definitely annihilates root 3, right? It sends it to 0. To be sure that it's the irreducible polynomial, I need to know that there's not some smaller polynomial which also kills root 3. The only possibility would be something like x plus beta, where beta is something in Q adjoin root 2, which would indicate that if I plug it in, I get square root of 3 plus beta equal to 0, which means that the square root of 3 is equal to like a plus b root 2. I guess you might put minuses here, but I mean, you see what I'm saying? I mean, this would imply this kind of equality, but that's impossible. You can't have root 3 reproduced by a rational linear combination of root 2. Right? That's a Math 200. I mean, I won't make you prove this. I think this is clear from Math 200, which we've all had or taught once upon a time. In the time before Soprano, but it's a long time for me. So anyway, that's how I know that this step up here is legitimate, because if once I know that root 3 has degree 2, that means that the extension field takes as a basis 1 and root 3. Because like root 3 squared is the same order as the irreducible polynomial, so that theorem we have, let me find it for a second, I'll tell you which theorem I'm talking about. Oh, so many things open. Is this it? Yeah. Ah, too close. This is the theorem, this one. This is the theorem that says if you have a simple extension of a field F with alpha algebraic, then anything in the extension can be written as a linear combination of up to the n minus 1th power of the extending element. Right? So this is something I'm using this in the case n equals 2, basically, b naught plus b1 times the square root of, what was it, 3? Where the b naught and b1 are taken from the field. In this case, the field in the problem we were just looking at is Q adjoin the square root of 2. But you must keep this theorem in mind, and I think I said its corollary is that 1 alpha squared alpha to the n minus 1 forms a basis for that simple extension. So we can use that theorem. Oh, let me go back to my, if I can find it. Oh, well, thank you. Merry Christmas to me. Let's see here. So, I mean, all I have so far is that set 1, root 2, root 3, root 6 forms a spanning set for the extension field, right? Now, I could try to prove linear independence of those directly, but that just seems... No, I don't want to do that. That's Math 200. That's that same thing I was just skipping over, proving that you can't write the square root of 2 as the square root of 3 rational combination of, I mean, like, the details of that is stuff we haven't really gotten into, and it's not, So we want a different way, which is just to use this theorem. We're taking Q, we're extending by root 2, and then we're extending by root 3. We got this tower of fields. And theorem 31.4, I think, is this one. So it's the extending the extension field thing, multiply the degrees, right? So like this, if we adjoin root 3 to this base field, and here we're adjoining root 2 to the base field Q. So this is the theorem that says that the product of their degrees is equal to the degree of the total extension, which is 4. Okay, so we know that the dimension of F, which is this thing, over Q is 4. We've got a set with 4 elements in it, so it follows that it's a basis. So, all right. I hope you guys got that one. Well, I mean, that one's kind of, the square root of 18 is messing with you, right? If you just tried to calculate directly, it would have been easy to spend a lot of time on this problem. But eventually, you should have simplified things down until you got to where I got, right? There's a less elegant solution, which is also correct. This one, man, I don't know what's the right way to go about this. Here's the way I did it anyway. I just said, okay, I'm going to find, I believe that theorem by Steinitz. This is a characteristic zero field, and it's an algebraic extension. Therefore, it is a simple extension. It's just a matter of finding out of what. And so to find out of what, well, I guess it is the of what's given to you right here, right? But the question is, what degree is that over Q? That's not immediately obvious. And so what I did was just to remove the radicals, right? And if you remove the radicals, eventually you get to this polynomial, which is quartic, which does not play nicely with Eisenstein, and it will thwart your efforts with mod 2. It's no help either. But when I got to mod 3, hooray. See, mod 3, 1, 1, 1. So modulo 3, this polynomial has no 0, which then, by our earlier theorem, implies that this polynomial is irreducible over Q. Remember that one? Yeah. So I had to do a mod 3 reduction. I don't know. Anyway, so once I have that, then I know that my extension field has degree 4 over Q. And I know that the basis is given by 1 alpha, alpha squared, and alpha cubed by that theorem I pointed back to you guys in the notes, because we know that, this is an irreducible polynomial over the rationals, and consequently, I mean, over the base field, I should say, to be more abstract. And here the base field is the rational number, so that's a basis. And of course, you could write it out in detail, but I just chose to write it like that because I'm lazy. But on the other hand, if you believe the homework problem from Galilean, it's also true that this is equal to that, right? So an alternative basis would be this, 1, root 2, root 3, root 6. So either would be, I mean, there's kind of two different ways of doing this problem, right? You could prove that this is equal to that. And then just the basis for this is obviously that, because I think we just did that in the previous problem. So. 7 was easy. So like square root of 2 times the square root of 3 is the square root of 6. So this is really just adjoining the square root of 6. And so, 1 root 6 is a basis for that. Kind of. This one's kind of anticlimactic. I was like, is there a comma missing here? No, there's no comma. A comma would make this boring. It's already been asked, right? But you like that one? Yeah. This one stung a little. At first, I thought it was boring. It seemed like number 3 all over again. I mean, it leads with the cube root of 24 is already in there, so we can drop that, you know. And we just need to look at cube root 3, cube root 6 adjoined to q. It's like, okay. So then that's, of course, you can look at it as the cube root of 2, then extended by the cube root of 6. So the first thing I need is basically that the cube root of x cubed minus 6 is irreducible over the base field q adjoining the cube root of 2 in order to like get started on the expansion that I usually do. And well, I mean, the fact that this is 0, that's not hard, right? I mean, that's why I wrote this down. But I'm claiming it's irreducible here, but I haven't shown it yet. All right. So to prove, this is a claim, right? So to prove that f of x is irreducible, I note that x cubed minus 6 is irreducible over q. Now I needed that it's irreducible over q adjoined cube root of 2. This is bad. I should have over q adjoined cube root of 2, you know? So take off a point right here for that being specific. But this is irreducible over q by Eisenstein with p equals 2 or Eisenstein with p equals 3. Pick your poison. As far as I know, we don't have Eisenstein for q adjoined square root of 2. I wish we did, but I don't believe we do. So sorry. Eisenstein is for base field of q. Yeah? Not base field of q adjoining cube root of 2. So we have to do other things there. We have to resort to other kinds of arguments. So here's my, here's the poison I picked. I just said, okay, if it does have a reduction, it has to be like this. X plus alpha times x squared plus beta x plus gamma. Here, either alpha or one of beta and gamma have to be in q adjoining cube root 2. Otherwise, if these are both integer polynomials, that contradicts the irreducibility over the rationals. So if there is a factoring, it has to be happening in the extension field by the cube root of 2. So that's where I'm looking for. This alpha, beta, gamma, all in q adjoin. They have to be irrational. So then I multiply it out. And that gives me these equations. In particular, alpha plus beta is 0, alpha beta plus gamma 0, and alpha gamma minus 6. Now, this one gives you alpha equal minus beta. Then you plug that into this. That gives you gamma equal minus alpha beta, which is equal to alpha squared. And then finally, we get alpha gamma is alpha cubed equal minus 6. Aha, well, alpha is just the cube root minus the cube root of 6. And minus the cube root of 6 is not in here. So you can't factor it. Consequently, the polynomial is irreducible over q adjoining square root of cube root of 2. I don't think that's immediately obvious, but here's the proof of it. And once you know that, then you know that q adjoin cube root of 2 extended by the cube root of 3 is a degree 3 extension because this is its irreducible polynomial. And as I said, on second thought, this is not number 3 all over again. Number 3 was much easier to prove that, you know, you guys, if there's any gap in your homework, it's that you didn't prove the irreducibility, right? You just assumed it. Am I right? Yeah, okay. Wishful thinking. But that's why I write these solutions, you know, because, you know, doing the homework, we don't expect to everybody do their homework perfect this first time. It's a learning experience, right? So hopefully you learn. Anyway, we've just shown that this is 3. And so then that means that this looks like these kind of combinations, which in detail looks like this in terms of rational coefficients, which looks like this in terms of rational coefficients. And by the way, same usual song and dance, this cube root 3, cube root 6, do I want to Oh, I said 3 when I meant 6 somewhere. I'm sorry, guys. But anyway, so this over the q adjoining cube root 2, that's degree 3. That's the thing I just showed on the previous page. And then using the theorem, this over q is this over that, and then that over q. Again, I think that's theorem 31.4 in Fraley, but that's 3 times 3, which is 9. Now the proof that cube root 2 is degree 3 over q is much easier because we can use Eisenstein, right? I mean, I don't need to do so much for this one because x cubed minus 2 is irreducible over q by Eisenstein with p equals to 2. And again, this is an abusive language. I should say irreducible over q. Because as you can see, there's a danger for confusion, right? And there's your basis. All 9 of them. 9-dimensional extension field over the rationals. Well, any questions about this one? Number 10. What do I got here? Find the degree and basis for q adjoining square root of 2 adjoining square root of 6 over q adjoining square root of 3. Let's see here. So I said square root of 6 is the square root of 2 times the square root of 3. Thus, q adjoining square root of 3 adjoining square root of 2 contains the square root of 6. So I say is consequently q adjoining root 2 root 6 is just q adjoining root 3 extended by root 2. And we argued that x squared minus 3 is irreducible over q adjoining root 2. Pretty much the same argument shows that x squared minus 2 is irreducible over q adjoining root 3, which is to say that this has degree 2. Which is to say that 1 root 2 serves as the basis of this over that. You know. So I'm using my previous homework problems to, I mean, this isn't quite a complete solution. I got tired. Sorry. In fact, I got so tired that I didn't write a solution to this one yet. So anyway, but I'm pretty sure I gave you a hint. Blaine, did it work?
Yes, it seemed to.
Okay, it seemed to. But anyway, I'll try to remember my hint because it doesn't come to me at the moment. Yeah, you read it. I'll read it back. In the meantime, I will be eating a delicious cookie.
Problem 138. My first move would be to assume all data in the problem and then try for a contradiction, namely that p of x has a 0.
So assume p of x has a 0 after you assume all this stuff. If p of x has a 0, that implies what? Oh, it would imply that implies the existence of an intermediate field, because if it has a 0, then, well, anyway. But I will finish the solutions. I just haven't done it yet. So anyway, that's all I got to project. So I'll put this away. And we still got 15 minutes. So is there any particular one you guys want to work on? Wow, you just took a beating. Consolidate some of my cookies. Looks like I'm gonna have to go back to Walmart and get some more. Yeah, I discovered these Linzers recently. I really like these. They have raspberry in them. Pretty good. Jenny's like, so if They don't all get eaten. They're going to your office, aren't they? Like, yeah, it's true. It's a side benefit of this project. Oh, so you guys had a question? I have a suspicion the ones I haven't written solutions to, some of them are pretty easy, right? From the previous section. Famous last words. I can go back to 29 and try to work some of those. Which ones did I assign you guys? I don't have them memorized. Oh, yeah. Where am I going to be? Centerboard? Okay. I had it big so I couldn't mess it up. Because I keep doing that. Did I assign like number 8? Let's do number 8. Actually, let me. 5 and 7. I'll try number 8. Number 8 is I'm supposed to. I've got alpha equal to the square root of 2 plus I, right? And I'm supposed to find the irreducible polynomial of alpha over q and the degree of alpha over q for the given algebraic number, and be prepared to prove your polynomials are irreducible over q if challenged to do so. All right. By the way, I was quibbling over the algebraic numbers. Are they inside R or are they inside C? They're inside C. I was talking about the algebraic extension of the rationals inside R. I mean, you could do that, but when people talk about algebraic numbers, they're talking about the algebraic closure of the rationals inside the complex numbers. That's the context. I was unsure about it when we had the lecture on that. Anyway, that doesn't really matter much to this, I guess. I think I'm about on markers. So what would you guys do with this problem? Like, basically, I don't have a strong sense of it. I mean, just start squaring. I think I would say alpha minus root 2 equals to I. Square that. Of course, I squared is minus 1. And so I get alpha squared minus 2 alpha root 2 plus 2 equals to minus 1. Isolate the radical again, right? So 2 alpha root 2 equals to, what is that, minus 3? Minus alpha squared, square that thing. You get 4 alpha squared times 2 equals to 9. Well, let me second here. Minus 3 minus alpha squared, which I believe is 9 plus 6 alpha squared plus alpha to the 4th. So this is, of course, 8 alpha squared. So that shows me p of x equal to, what is it, x to the 4th minus 2x squared plus 9 annihilates alpha. In other words, p of alpha is equal to 0 by construction, right? I mean, these steps I did were reversible is the point, right? Like this is... You got to be careful. If you did a step which wasn't reversible, then I wouldn't know for sure that when I plug in alpha, it was a 0. But here these steps are reversible, so I know it. I need what else? I need to know it's irreducible, right? Now here's a question I don't know the answer to. Is it possible to do this kind of algebra and come up with something which is not irreducible? I don't know. Every time I've done this so far in this course, it's been irreducible. I don't know, I guess if you go too far, like if you square beyond what you need to, you could end up creating a higher order polynomial by accident if you just didn't see it for what it was. Something like that. Can you guys tell me why this is irreducible? Ah, man, Eisenstein isn't going to help us, is it? because we've got like a 2 and versus a 3 squared. The primes aren't common in the coefficients. It's no help. Looks like we're going to have to do some sort of modular arithmetic reduction to see irreducibility. So I would try, my next move would be try mod 2, right? So P of 0, 0, 0, 9, which is 1. How about if I plug in 1 into the reduction, get 1 minus 2 plus 9, which is it's 0. Is it 0? It's 8. Which is 0. Curses. That doesn't mean that it reduces. That just means that mod 2 reduction test didn't work, right? We just have to find 1. Yep. I mean, you could go to mod 17 if you want. I don't recommend it. Yeah, mod 3 is a good choice. So, sometimes it's helpful to write down, just for your mental purposes, this is really x to the 4th plus x squared. Oh, yeah. You're right. That's not going to work, is it? Is that what you're saying? Yeah. Yeah. Curses that. Mod 4. We got P of x. X to the... What was I saying about this homework being easy? Maybe I was wrong. I'll do plus 2x squared. I like to keep it positive. And it's plus 1. Is that x squared plus 1 squared? That's x squared. That's x squared plus 1 squared. Dang. Now I'm left. These are the only tools I have in my toolbox at the moment, guys. Is Eisenstein's criteria and the mod p reduction. Do we have another tool? Am I forgetting something? As far as I can remember, that's all my. What time? You guys gotta tell me when it's 5:30 because I gotta stop. 5:24. Okay, so we're cool. Well, let's try 5. Let's try 5. It's starting to get hurtful. P of x. I'm glad that we, this has shown something though, that which is that reducing the coefficients modulo the thing and then looking for factorization saves us a lot of time. I hadn't noticed that until just now, so yay. I'm learning. X to the 4th. I mean, maybe I noticed it, but I forgot. I don't know. Whatever. Fine. I'll deal with the minus 2 x squared, and then that's minus 1. Right? Plus 9 is minus 1. Does that? Please don't tell me that factors. Does that factor? Okay, good. Oh, let's just plug in numbers if we don't see it right off. So plug in 0, minus 1, plug in 1. We get 1 minus 2 minus 1, which is minus 2. Plug in 2, 16 minus 16 minus 1. Plug in 3, 81 minus 2 times 9 minus 1. 5 is pretty nice, by the way, because 5, we know how to do arithmetic with 5, like, pretty well. Most of us are pretty good at arithmetic mod 5. It's a good choice. Maybe a better choice than even 4 or 3, Anyway, so this is a subtraction of 19 from 81. It's not equal to 0, right? I don't care what it is. It's not a multiple of 5. If I plug in 4, Oh, I'm dumb. I'm dumb. Check it out, right? Because this is polynomial is even, right? This is an even polynomial. So P of C is equal to P of minus C. If I check 1, I've already checked minus 1. If I check 2, I've already checked minus 2. 3 is minus 2, mod 5. So, in fact, this is also equal to minus 1. Which I guess we would to check. Well, that's... Yeah, 2. Uh-oh. Maybe I made a mistake.
I think we have a problem with R2. 16, it should be minus 8.
Oh, thank you, thank you. They're both 2. Okay. Excellent. Anyway, more importantly, they're not 0. Consequently, we have found Z mod P in which the polynomial is irreducible, and then by the theorem from an earlier, when we were still in Galilean, there's a theorem which says what? That implies that P of x, so P of x, the reduced polynomial P of x irreducible over Z5 implies that P of x irreducible over Q. This is the theorem that I have proved in the notes. It involves the arguments with content and other things. But yeah. Ouch. That one hurt a little. And I thought this was going to be an easy problem. So I picked the bad one. Oh, I didn't assign this one. Ah, I should have.
What were you saying about the previous moduluses doing that work help you? Like seeing the reductions. You're saying calculating those previous.
Oh well, see the other. Well, yeah, because this once you see that, then it's not irreducible, mod 3. Okay. Because there's a reduction.
Oh, I see.
So I don't need to plug in 0, 1, and 2 to see what happens.
Oh, okay. Yeah.
You know.
So it's not okay.
I mean, mod 2, even if I was smarter. What does this reduce to mod 2? It's P of x is equal to P of x mod 2 was x to the 4th plus 9, but plus 9 is minus 1, which is x squared minus 1. Now at this point, this is easier. I mean, plugging in 0, plugging in 1 is always easy. So the payoff isn't that big, mod 2, but.
I thought you were saying, oh, it's a good thing.
Yeah, so to sort of summarize, calculationally what's going on here, I mean, to really understand the field extension problems that we're looking at, we have to understand when is a polynomial irreducible, right? So I guess the irreducibility theory, when we were looking at it, it didn't seem particularly exciting, right? I mean, it's just kind of like these, who cares if a polynomial is irreducible over Q theorems? But the reason we care is because it's all about how tall these field extensions are, basically. And these are our tools to figure that out. But, yep, I must go. As my wife made a somewhat sarcastic comment about me getting home at 7 today. So I view that as an indirect way of telling me to get home earlier.
It's a challenge.
I could be. No, I'm not wrong.